In the vast quiet of the cosmos, where light drifts like ancient breath across an ocean of darkness, the universe has always obeyed one simple rule. Everything moves from what has been toward what will be. Every photon, every ripple in space-time, every whisper of radiation carries the unmistakable signature of a story already written. Yet in that eternal tide, something appeared that did not belong. A thread of energy so faint it nearly dissolved into the background, and yet so precise it could not be mistaken for noise. A signal that moved against the current of time. Scientists would later describe the moment of detection as standing at the edge of a cosmic cliff staring into something that stared back. The data carried the spectral age of a universe older than our own, and yet encoded within it was a pattern for casting events that had not happened, in a cosmos that does not yet exist. It was as if time had folded inward, like a forgotten page pressed between unseen chapters, revealing an echo from a story humanity has not begun to write. In that impossible alignment of numbers and light, a quiet dread settled. For if the universe is a closed chronology, sealed by the forward arrow of entropy, how could anything arrive from a world not yet formed? What does it mean when causality falters, when the future speaks before its birth, when existence itself bends under the weight of its own reflection? The signal did not answer these questions. It merely arrived, steady, deliberate, indifferent, leaving humanity to wonder whether it was a message, or a consequence of a deeper reality we have never imagined. In the quiet, methodical rhythm of scientific work, discovery rarely announces itself with grandeur. It arrives instead as a whisper and anomaly buried beneath mountains of expected data. A subtle deviation overlooked 1,000 times before finally revealing its weight. That is how the signal first emerged, not as a revelation, but as a blemish. A thin, fragile thread of order stitched, possibly into the cosmic noise. The observatory responsible for the first detection was not searching for mysteries. It was one of many Earth-based nodes participating in a global effort to refine measurements of the cosmic. Microwave background, the faint relic radiation left from the universe's earliest moments. Its instruments were tuned to observe the faint anisotropies. The temperature variations scattered across the sky like fossilized fingerprints of creation. These signatures, mapped by satellites like COBE, WMAP, and the Planck Observatory, are among the most ancient forms of light in existence. They drifted through the expanding universe for 13.8 billion years, carrying within them the structural memory of everything that would become galaxies, clusters, and the great cosmic web. On the morning the anomaly appeared, the team on duty at the facility was performing what they believed to be routine cross-calibration. The observatory was situated in a high-altitude desert plateau, a place chosen for its dry air, low radio interference, and vast open sky. At dawn, the horizon glowed faintly orange, and the instruments still cold from the night hummed in a mechanical chorus as they gathered the universe's most ancient light. The researchers were not expecting anything unusual. For months, their goal had simply been to refine the local noise model and compare it with data gathered by the cutting edge Canadian Hydrogen Intensity Mapping Experiment, known as CHIME. The combination of microwave background data with low-frequency radio observations promised to deepen humanity's understanding of the early universe's structure. It was the kind of work that demanded patience, precision, and above all confidence that the cosmos would behave according to expectation. And then, inside the raw output of a calibration run, one of the analysts noticed a narrowband spike, just a thin, needle-like intrusion rising from the flat noise floor. It was small, almost negligible, an imperfection in the cosmic fabric. The analyst flagged it for review, believing it to be an artifact, perhaps a terrestrial radio leak, perhaps a reflection from a distant satellite skimming the horizon. But later that same day, the spike appeared again, this time in a separate dataset, collected hours apart, under different atmospheric conditions. It appeared precisely at the same frequency, a frequency no natural astrophysical source was known to occupy. Still, no one raised alarms. Space is full of interference, both from Earth and from the growing constellation of orbiting instruments that pepper the sky. The anomaly was placed into a queue for cross-checking. The team continued their measurements, but the universe has a strange way of repeating its secrets until someone finally listens. Over the next week, the narrowband spike re-emerged 16 times. Never loud, never bold, but perfectly consistent. Its shape was unmistakable. Its symmetry was unnatural. Its coherence was undeniable. Signals in the early universe are not coherent. They are smeared, stretched, battered by billions of years of expansion. Structure cannot survive the first microseconds of cosmic history, not in the way this anomaly presented it. And yet, there it was, a pattern woven into radiation believed to have originated mere hundreds of thousands of years after the Big Bang. A region where temperature fluctuations were measured in millionths of a degree. The anomaly did not fit. It was too sharp, too structured, too deliberate. Only when the team overlaid the anomaly across the Planck satellite's deep field archives did the full weight of the discovery begin to press upon them. The signal had been present for years, hidden, faint, and overlooked. Planck's instruments had caught pieces of it, but the data had been too weak to distinguish from noise. Now with SHIM's low-frequency sensitivity and LOFOR's extraordinary resolution working in parallel, a more complete shape began to emerge. It was not a random spike. It was a signature that seemed to pulse according to a harmonic pattern, a pattern that could not emerge naturally. From the chaotic plasma of the early universe, weeks turned into months as more observatories joined the investigation. LOFOR in Europe detected the same anomaly in a different portion of the sky. South Africa's Meerkat Array found it again, faint but unmistakable. And when several amateur radio astronomers began reporting similar narrowband features, the anomaly was no longer a knower. It had become undeniable. The first breakthrough. It came from a graduate researcher working late into the night. In an attempt to isolate the frequency into a cleaner dataset, she subtracted out known Earth-based interference using a weighted algorithm. The results surprised her. The anomaly persisted, but with an unexpected regularity. Not only was it narrowband, it exhibited periodic modulation, as if the signal were oscillating in a rhythm that did not match any known cosmic process. Cosmic radiation does not modulate. It does not encode. It does not behave. The graduate researcher submitted her findings quietly, attaching a note that simply read, "This should not be here." Scientists across several institutions began performing similar reductions. Every attempt to dismiss the signal as noise failed. Every model that treated it as an artifact collapsed. And as the pattern became clearer, something even more troubling surfaced. The signal showed a subtle drift in a direction opposite the expansion of the universe. Signals from the dawn of time stretch outward like threads pulled taut across the widening void. Their frequency should shift lower, dragged redward as the cosmos grows colder and larger. Yet this anomaly shifted slightly higher, as if being drawn inward towards something unseen. It was not obeying the expansion. It was resisting it. A signal resisting the universe's growth was unprecedented. Astrophysicists, cosmologists, particle theorists all attempted to reconcile the data with known physics. Some tried modeling it as a gravitational lensing echo. Others proposed exotic foreground emission. A few speculated about scattering from hydrogen structures in the cosmic web. But each explanation failed under scrutiny. The first scientist to propose something radical was not a senior figure, but a relatively young cosmologist known for her work on early universe inflation theory. She presented the possibility that the signal was not formed within the context of our cosmic timeline at all. Instead, she argued, it might be a remnant of a pre-inflationary structure, something imprinted. Before the universe underwent its exponential expansion, such a hypothesis was already unorthodox. Pre-inflationary imprints should not exist. Inflation wipes the slate clean. But even this extreme idea could not explain the signals. Coherence, the second radical suggestion, came from a more established physicist working with data from the Wilkinson microwave anisotropy probe. He pointed out that the periodicity in the anomaly resembled predictions of certain multiverse collision models, scenarios in which neighboring universes interact through the higher dimensional fabric of inflationary fields. However, even he admitted such interactions should not produce coherent narrowband signals. They would appear as large-scale deformations, not precise oscillations. It was the third suggestion quietly proposed in a draft. Paper on Arxivvat caused the first ripple of shock through the scientific community. The author, a specialist in quantum cosmology, suggested that the frequency pattern bore resemblance to predictive markers used in simulations of future OPEC universes. The possibility, he wrote, was faint but mathematically intriguing. The signal might be carrying information belonging not to an ancient world, but to a possible descendant universe. A universe emerging after this one has long collapsed. A universe not yet created. When the draft paper circulated, many dismissed it immediately. The idea of information traveling across cosmic generations was considered impossible. The laws of thermodynamics forbid such an exchange. Causality forbids such communication. Even speculative theories of eternal inflation do not allow clean transmission of data from one universe to the next. Yet the anomaly refused to collapse under scrutiny, and so the question began to linger quietly at first, then more boldly as more observatories added their weight to the investigation. What if the signal was not from the early universe at all? What if it was merely embedded within ancient radiation because it had traveled through the deeper layers of space-time? This was not the kind of idea science entertained lightly. It required confronting the possibility that time is not linear, that universes do not exist in isolation, and that space-time might permit connections across unimaginable distances, not just in space, but across the boundaries of existence itself. Months into the investigation, the researchers gathered for a coordinated review. Representatives from NASA, the European Space Agency, and several leading universities participated. They compared data from Planck, WMAP, CHIME, LOFER, Meerkat, and the Atacama Cosmology Telescope. The anomaly lined up across all datasets. The signal was real. It was coherent. It was structured. And it was not explainable by any known mechanism. Slowly, reluctantly, the scientific world accepted that something had been detected, something that stood outside current cosmology. The signal was no longer a curiosity. It had become an intrusion as the pieces came together. The implications grew stranger and heavier. The frequency modulation appeared to match theoretical predictions for a universe undergoing late-stage acceleration, a stage our own universe is expected to reach trillions of years from now. The encoded fluctuations mirrored the energy densities of a hypothetical post-dark energy epoch. The patterns aligned with a cosmological timeline that had not yet unfolded. With every new layer of analysis, the anomaly grew more unsettling. The universe was not just whispering something old. It was whispering something that had not happened. The scientists studying the anomaly found themselves facing a question that no model could satisfy. How can something enter our cosmic timeline carrying the signature of a future that has not occurred? For the first time, the discovery was no longer simply an observational puzzle. It had become a philosophical fracture, a doorway into a deeper understanding of reality, or a warning that human physics had only begun to scratch the surface of what time truly is. And so the search intensified, no longer driven by curiosity alone, but by the quiet fear that the signal represented a glimpse of something far larger, far stranger, and far closer than anyone had imagined. It began in a place for silence, an observatory perched on the edge of a barren plateau, where the winds seemed older than the mountains and the night sky stretched unbroken from one horizon to the other. The facility's instruments were designed not to look for anything spectacular, but to listen for the faintest traces of what remained after the universe was born. They were custodians of ancient whispers, relic photons from the cosmic microwave background. Radiation so old it carried the memory of the universe, when it was only a few 100,000 years into existence, inside the control room. The atmosphere was calm, almost ritualistic. Screens glowed with color-coded maps of the sky patchworks of blues and reds, representing minute temperature variations left behind by the primordial plasma. These slight anisotropies were not anomalies to be solved. They were expected, measured, cataloged for decades through missions like COBE, WMAP, and the Planck satellite. Their patterns helped shape humanity's understanding of how structure formed, how galaxies coalesced, how space-time expanded. The researchers on shift were engaged in routine work, calibrating noise models, cross-checking atmospheric corrections, comparing ground-based measurements with archived satellite data. It was a quiet task, filled with the kind of patience required when listening for signals almost erased by time itself. Most nights were uneventful, a confirmation that the universe remained consistent, predictable, and obedient to its own laws. But this night would be different. The anomaly first appeared as nothing more than a thin spike in a wide band of microwave noise, a narrow frequency rising too neatly, too sharply, too deliberately from what should have been a random sea of fluctuations. One analyst paused, adjusted the scale, and looked more closely. The spike remained. A single, slender, peak-like a needle-piercing and otherwise uniform surface. He marked it for later review, noting that it was likely terrestrial interference, perhaps a faint radio reflection from an airplane or bleed-through from an orbiting satellite. It had happened before, many times. The universe, despite its vastness, is often disturbed by the hum of human machinery. Hours later, during a second observation sweep, the spike reappeared. Same frequency, same amplitude, same shape. This time, there were no satellites above the horizon, no known radio traffic in the region, and no mechanical anomaly in the instrumentation. The analyst called over a colleague. They cleared local interference models and ran a diagnostic sweep. The spike remained, comfortably nestled within microwave background radiation nearly 14 billion years old. Still, they did not consider what it might represent. They treated it as an inconvenient something to remove, not something to investigate. But the universe does not hide forever from those who listen. Over the next several days, as the observatory continued its scheduled scans, the spike returned again and again. It appeared in different regions of the sky, yet always at the same frequency, always with the same coherence. When the team cross-compared results with external observatories, CHIME in Canada, LOFAR in Europe, Meerkat in South Africa, the pattern began to reveal itself more fully. The anomaly was not local, not instrumental, not a glitch. It was everywhere. A quiet, structured whisper woven through the cosmic microwave background. To understand the strangeness of such a discovery, one must remember that the early universe was a place of unimaginable violence. In the moments after the Big Bang, matter and radiation were fused into a seething, opaque plasma. No signal, no structure, no coherent pattern could survive those conditions. When the cosmos finally cooled enough for atoms to form, light was released in all directions, leaving behind the microwave background as a smooth, almost featureless glow. The radiation that astronomers detect today is stretched by billions of years of expansion. It is cold, diffuse, and chaotic. Nothing within it should appear deliberate. Nothing within it should appear ordered. Yet this signal was both. When the team finally isolated it, separating it from the noise through a combination of filtering algorithms, statistical analysis, and signal decomposition, a revelation emerged. The frequency was not random. It was modulated ever so slightly, as though carrying an internal structure. Not a message in any human sense, but a pattern, a periodicity inconsistent with natural astrophysical sources. Astrophysical signals, pulsars. Quasars, black hole jets do not embed themselves inside the very fabric of the cosmic microwave background. They exist on top of it, distinct and separable. But this anomaly seemed fused with it, as if it had been present since the beginning. The question began to grow quietly. Within the scientific community, how could something so structured survive the chaos of the early universe? As more observatories trained their instruments on the anomaly, a more troubling detail emerged. The frequency of the signal was drifting, not downward as expected from cosmic expansion, but slightly upward as though resisting the stretching of space. According to the standard cosmological model, All ancient signals stretch redward with time. They lose energy as the universe expands, becoming lower in frequency. But this signal seemed to do the opposite. It was as if it were being pulled from somewhere beyond the universe's expansion, or pushed by some hidden process. The researchers began reviewing possibilities. Was it natural? Unlikely, no known cosmic process created such narrow, coherent emissions from the early universe. Was it artificial? Impossible, no civilization existed billions of years before galaxies formed. Was it a glitch? Extensive cross-verification from independent observatories quickly eliminated that possibility. Still, the researchers hesitated to label it anything other than unknown. The scientific method demanded restraint. A mystery must survive every attempt to be disproven before it is permitted to exist. So they tried relentlessly to prove it was nothing. They compared archives from Planck and WMAP. The anomaly was faint. There. They correlated hydrogen line maps from CHIME. The frequency matched. They combed through Laufer's deep radio data, and again, faint remnants of the same structure appeared. Each match strengthened the anomaly's presence. Each confirmation stripped away another explanation. As the evidence solidified, the first true moment of unease began to settle. The anomaly did not behave like early universe radiation. It behaved like something imposed onto it, something coherent, patterned and immune to the decay of time. One night, during a particularly long data analysis session, a junior researcher noticed something disturbing. When she plotted the frequency drift across different observation dates, the pattern resembled not random variation, but a subtle harmonic curve. A curve that matched mathematical models describing a universe undergoing rapid acceleration far into its own future.
Ow!
It was as though the signal were carrying information not from the early cosmos, but from a distant epoch, trillions of years ahead, an epoch where dark energy dominated completely, driving space into an exponential stretch. Her report landed on the desk of the senior cosmologist leading the project. He examined the data silently, his expression shifting from curiosity to disbelief. He did not speak for several minutes. Finally, he said only, "Run it again." They did. Nothing changed. The curve remained. The harmonic signature persisted. The implication deepened as additional researchers joined the analysis. One comparison emerged repeatedly. The modulation pattern resembled predictions associated with simulations of successor universes.
Ow.
Those modeled in theories exploring the possibility of cosmic rebirth, vacuum decay, or transitions between phases of spacetime. Theoretical papers from arcs of once, relegated to speculative corners of cosmology, were suddenly being revisited with new urgency. Ideas once dismissed as thought experiments now offered the only frameworks that could interpret the anomaly's structure. Early universe physics could not explain it. Particle cosmology could not explain it. Traditional models of space-time offered no room for it. Slowly, and with palpable discomfort, the researchers began to contemplate the unthinkable. The signal might not have originated in the past. It might have entered the cosmic microwave background after the fact, threading itself into radiation older than stars or galaxies. Yet carrying the fingerprints of a future that had not occurred. Meetings grew longer. Emails grew more urgent. NASA, ESA, and multiple academic institutions formed working groups. Instruments were recalibrated, atmospheric contamination models refined. Instrumental drift analyzed down to the microkelvin. Yet every attempt to dismiss the anomaly only hardened its presence. The signal appeared coherent. The signal appeared structured. The signal appeared impossible. When a senior researcher finally presented the collective findings at an international symposium, the room fell silent. The data was compelling. The signal carried traits inconsistent with early universe origins. Its modulation aligned with energy densities predicted for epochs far beyond the current age of the cosmos. Its coherence defied scattering processes, known to erase structure in the first moments after the Big Bang, and yet it existed, embedded in the most ancient light ever seen. After the presentation, one scientist asked quietly, "If the signal isn't from our past, where is it from?" No one answered. No one could. The anomaly had crossed a threshold. It was no longer an observational curiosity. It was a philosophical wound carved into the foundations of cosmology. It challenged the arrow of time. It questioned the separation between universes. It hinted at communication or consequence across boundaries no theory fully described in the days that followed. As analysis deepened and instruments continued to listen, one truth became impossible to ignore. The universe had spoken. But not in the voice of its beginning, in the voice of something waiting to exist and humanity. For the first time stood at the crossroads between what was known and what might be reaching out from a future not yet born. There comes a moment in every scientific investigation when the data stops whispering and begins to pull. When a discovery bends so far beyond precedent that those who study it feel the weight of something larger than themselves, quiet shiver at the edge of understanding. For the researchers analyzing the anomaly, that moment arrived when they traced its frequency signature backward, deep into the earliest possible moments of cosmic history. The pattern did not originate from a star, a nebula, or any known astrophysical event. It did not resemble the emission of hydrogen clouds, nor the rhythm of pulsars, nor the faint static of distant quasars. Instead, the signal appeared embedded within the cosmic microwave background at a depth so profound that its presence seemed absurd. When mapped onto the timeline of the universe, the structure correlated not with epochs of formation, but with a period before formation was possible, an era preceding cosmic inflation, when space-time had not yet expanded into the form recognizable today. To grasp the enormity of this discovery, one must remember what the universe was before inflation. In those first instants, less than a trillionth of a second after the Big Bang, the cosmos existed in a state beyond human imagination, a quantum haze where temperature and density approached infinity, where the laws of physics as understood today dissolved into chaos. In this realm, no pattern could endure, no signal could propagate, no structure could survive the violent blooming of inflation, during which the universe expanded faster than the speed of light, stretching microscopic fluctuations across unimaginable distances. Inflation was a cosmic eraser. It wiped the slate clean, and yet the anomaly lived beneath it, coherent, ordered, deliberate. Something that should not have survived entered the universe, carrying a frequency too precise to be dismissed as chance. The implications settled over the research teams like a cold fog. If the signal precedes inflation, then it defies not only observation, but the entire cosmological model built over the last century. The shock deepened when a group of theoretical physicists attempted to model the modulation pattern mathematically, expecting noise or random periodicity. They instead discovered something disturbing. The encoded fluctuations aligned with equations, describing a far future stage of the universe, one dominated by dark energy. Long after stars have faded and matter has thinned to dust, the signal did not resemble the signatures of the past. It resembled the predictions of the future. The room where this conclusion was first presented fell silent. Researchers stared at plots that seemed to contradict the arrow of time itself, a signal that both predates inflation and mirrors the physics of a universe not yet born. It was a paradox so pure that even the language of science struggled to contain it. The researchers understood immediately what the data implied, even if they refused to voice it aloud. If the signal carried the mathematical fingerprint of a future epoch, then either their models were catastrophically flawed, or the universe was communicating through mechanisms not yet discovered. The anomaly appeared to originate from a world that did not yet exist, and one that might emerge only after this universe has reached its end. Causality, the most fundamental principle in physics, was the first casualty of this revelation. The arrow of time, as described by thermodynamics, flows from order to disorder, from low entropy to high. Information cannot move backward along that river. It cannot emerge from the end and deposit itself at the beginning. Yet the signal seemed indifferent to this rule, as if entropy were not a boundary but a veil that could be crossed. Relativity, too, was challenged. Einstein's framework forbids faster-than-light communication and prohibits signals from traveling through space-time in a way that disrupts chronological order. But the anomaly did not appear to travel through space-time at all. It was embedded into the very background radiation itself, as though it had been placed there by an unknown mechanism outside the flow of time. The scientific community fractured. Some dismissed the discovery as a calibration error that had somehow passed through the most rigorous scrutiny in modern astronomy. Others suggested that it was an artifact created by interference between observatories. Even though cross-correlation had eliminated that possibility, a few invoked unknown astrophysical sources objects, or fields yet to be discovered but none could explain the coherence or the pre-inflationary signature. And then there were those who entertained a more unsettling possibility, that the anomaly represented a multiversal overlap in the inflationary model of cosmology. New universes may be continually forming in a vast expanding field. Each bubble universe undergoes its own inflation, creates its own space-time, and evolves independently. Most remain forever out of contact with one another. But in rare scenarios theorized by mathematical physicists, the boundaries between universes might thin or interact. If two universes touched, even briefly, they could imprint echoes onto one another. Most predicted such imprints would be large-scale distortions, not coherent signals. Yet the anomaly defied all expectations, as though structured information had slipped through the boundary of existence. Quiet tensions spread through the global network of researchers. For the first time in modern cosmology, the data suggested something fundamentally impossible. If the anomaly was genuine, then humanity had observed an event that did not belong within the confines of its own universe. The shock of that implication rippled through conferences, workshops, and late-night discussions. A few whispered, almost reluctantly, that this might be the first empirical evidence that the multiverse is not merely theoretical, interactive. But even that explanation fell short. The modulation of the signal did not resemble any known signature of multiverse collision models. Instead, its pattern mirrored predictions associated with a future epoch of cosmic evolution, a universe trillions of years ahead. A universe no physicist expected to communicate across the gulf of existence. A universe that had not been created. The tension grew heavier when a new analysis revealed something even stranger. When researchers simulated the future evolution of the cosmos, using dark energy models, they noticed that the anomaly's modulation matched the predicted oscillation of scalar fields, expected to dominate the universe's far future dynamics. This could not be coincidence. The alignment was too precise. It was as if the signal were calibrated to conditions not of the early universe, but of its distant, inevitable fate, in laboratories and observatories around the world. Disbelief hardened into something deeper. A recognition that the anomaly did not simply break a rule. It broke the foundational concept of time as a one-directional flow. It fractured the chronology of the universe. The first formal proposal describing the discovery used measured language, cautious phrasing, and dozens of caveats. But between its lines lay the fear scientists dared not write outright. If a signal exists that appears older than the universe, yet carries the physics of its future, then something beyond known space-time has reached into the cosmic microwave background and placed it there. The data resisted every attempt to invalidate it, resisted every explanation, resisted the entire framework of cosmology. Some researchers retreated into skepticism, refusing to accept a phenomenon with consequences too vast to contemplate. Others pushed deeper into theoretical models, exploring whether exotic mechanisms, closed time-like curves, quantum gravity effects, or hypothetical tunneling between vacuum states might allow information to bypass chronological order. Many of these models were speculative, uncertain, and beyond empirical reach. But for the first time, they offered pathways through which the anomaly could exist. Even these theories, however, confronted a limitation. None accounted for a signal that appeared within radiation older than galaxies, encoded with predictions of a future universe. None explained how such information could survive inflation. None explained how coherence could be preserved across cosmic epochs. The shock turned to quiet dread when one group proposed a radical interpretation, that the signal might represent a boundary condition from a cyclical universe model, a universe that collapses and is reborn. with information passing from one iteration to the next. In such models, the death of one cosmos seeds the creation of another. But these ideas remained speculative and lacked empirical validation. They were metaphors more than models, hopeful bridges across gaps too wide for current physics to span. Still, the anomaly persisted, unyielding, uninterpretable, unbound by the laws it violated, as debates continued. The tone of the scientific community shifted. No longer was the anomaly dismissed as noise or artifact. It had passed those tests. Now, it was something else, something neither accepted nor rejected, suspended in a liminal state between discovery and impossibility. A paradox that demanded explanation, but offered none. In the long, contemplative silence of research offices around the world, a deeper realization began to form. If this signal truly carried the imprint of a universe not yet created, then humanity was not merely interpreting cosmic history. It was witnessing cosmic destiny, an echo of a future reality touching the present. This realization frightened even those most willing to explore speculative ideas, because if time is not a closed sequence, if information can flow from the future to the past, then the universe is not the linear story humans believed it to be. It is something more fluid, more interconnected, more aware. Some physicists whispered that the anomaly might represent a deeper structure of reality, scaffolding beneath spacetime, where future and past are not separate regions, but entangled states of a larger, timeless whole. Others warned against anthropomorphizing the cosmos, insisting that the anomaly might be a mathematical artifact of unknown physics rather than a deliberate signal. Yet the unease remained. Scientists felt it in the late hours, staring at data that refused to fit the universe they understood. A quiet, unsettling truth lingered at the edges of their calculations. If the anomaly was real, then human physics had reached its boundary. Beyond it lay something vast and unreachable, and in that recognition emerged the first hint of awe. Awe tinged with fear, awe rooted in humility. Awe born from the possibility that the anomaly represented not a mistake, but a message carved into the universe's oldest light, a message not from the past, but from what must still come to be. Thus began the age of scientific shock, an age where humanity confronted for the first time the possibility that the cosmos might not simply expand through time, but speak across it in science. There are discoveries that require no more than a moment's confirmation clear, unambiguous signatures that demand attention the instant they appear. The anomaly was nothing like that. It was quiet, evasive, and buried so deeply within ancient light that even the most sensitive instruments nearly missed it. When its outlines finally emerged, it did so reluctantly, as if the universe were allowing only fragments of a story far greater than human understanding. And once those fragments were seen, they could not be ignored. Months passed as researchers returned to the beginning, to the rawest datasets from every observatory capable of detecting such faint whispers. They peeled back layers of noise, recalibrated detectors, corrected for atmospheric distortion, thermal drift, electromagnetic interference, and even the gravitational pull of the moon. Teams at Chime rebuilt their filtering algorithms from scratch. Laufer reprocessed archived scans stretching back years. The Atacama Cosmology Telescope in Chile repeated observations under different sky conditions. JWST, not designed for such frequencies, was nonetheless queried for potential infrared correlations. None were found. But the effort reflected the urgency that now permeated the global scientific community. The signal endured. It did not weaken. It did not scatter. It did not dissolve beneath scrutiny. Instead, it sharpened. Each new instrument added its own clarity to the growing portrait of the anomaly. What had once appeared as a thin spike in microwave noise now revealed itself as a layered structure, repeating intervals woven into a framework so precise that chance was no longer plausible. The repetition was subtle, nearly lost in the data, yet unmistakably intentional in its regularity. Not a message in any human sense, but something encoded, something with internal rhythm. The repetition cycle, became the first breakthrough. It was not random. The interval between modulations fit a curve predicted by cosmological models describing a universe in deep, late-stage acceleration, a universe where dark energy has overwhelmed all other forces, stretching space-time at an ever-increasing rate. Such epochs lie trillions of years ahead, long after the last stars flicker into darkness. Yet the signal behaved as though it were shaped by them. Researchers hesitated to voice the conclusion. The implication was too extraordinary, too disruptive. The idea that the modulation of the signal corresponded to physics existing only in the universe's distant future was nearly unthinkable. But the data persisted. Every cross-check confirmed it. Every simulation reaffirmed it. And soon, another layer began to surface. When the team analyzed minute fluctuations in the signal, teeny shifts in amplitude and frequency, they discovered patterns predicted in models of hypothetical successor universes, theoretical constructs proposed in studies of cosmic transitions, vacuum decay, or cyclical cosmology. These models describe universes born not from nothing, but from the remnants of others. Universes that inherit physical conditions from predecessors, or imprint faint signatures. Across boundaries of spatian, the fluctuations within the anomaly matched them with eerie accuracy. They aligned with energy densities expected in a newly formed universe. They reflected scalar field oscillations predicted during cosmic reheating cycles. They resembled the theoretical fingerprints of a universe beginning rather than ending. This was not coincidence. This was architecture. The research teams began to split into factions, not by disagreement, but by focus. Some chased the mathematical implications of the anomaly's harmonic structure. Others analyzed noise simulations to ensure no earthly contamination could mimic such precision. Particle theorists examined whether exotic field Zaxians, inflatons, or vacuum fluctuations could generate similar signatures. And a smaller, more cautious group explored a possibility that had long existed only at the edges of speculative physics: inter-universal communication. For decades, quantum cosmology had proposed that space-time might be more complex than the smooth continuum described by general relativity. At microscopic scales, it could unravel into quantum foma, turbulent landscape where virtual particles erupted and vanished, where geometry twisted, fluctuated, and recombined. In such environments, quantum information might behave in ways inaccessible to classical physics. Some theories suggested that universes might share deep geometric connections, like adjacent layers in a higher dimensional structure. Others imagined tunnels through which information could leak, subtle, faint but detectable under the right conditions. For most scientists, these ideas were philosophical curiosities, elegant mathematics without experimental grounding. But now, with a coherent signal embedded in the oldest light in the universe, these once dismissed theories gained sudden urgency. The community began to ask a question they were not prepared to confront: if the anomaly did not travel backward through time as humans understand it, then how did it arrive? A number of physicists argued that backward travel was the wrong concept entirely. In classical space-time, information must follow geodesics, curved paths determined by gravitational fields. But the anomaly did not follow such paths. It appeared everywhere at once, equally present in all regions of the cosmic microwave background. That ubiquity meant the signal had not traveled through space. It had been placed there, distributed uniformly across the sky. This realization reshaped the entire investigation. The anomaly was not a signal passing from point to point. It was a global imprint. Whatever created it did not move through space-time. It operated on space-time. This forced researchers into deeper theoretical waters in quantum gravity models. Space-time is not a static arena, but a dynamic entity. It can stretch, ripple, fold, or even tear. Some theories propose that the geometry of one universe may influence another at points of extreme density or curvature. In multiverse models derived from eternal inflation, countless bubble universes expand within an inflating field, sometimes brushing against one another. These collisions could leave imprint circles in the cosmic microwave background, oddly shaped temperature anomalies, or faint signatures visible across the sky. Yet the anomaly did not resemble any predicted pattern of bubble collisions. It bore the sophistication of a frequency-modulated structure, not a spatial deformation. One researcher proposed a radical solution. Perhaps the signal was not the result of a collision at all. Perhaps it was a resonance and interference, pattern produced by the overlapping vibrations of universes existing within a deeper shared geometry. Not separate bubbles, but harmonics in a cosmic symphony far broader than the observable universe. This idea gained traction when simulations revealed that certain multiversal models predict coherent fluctuations. When universes with similar physical constants interact across dimensional boundaries. In theory, these resonances could encode information accidentally, not deliberately, and imprint them onto regions of space-time. If this were true, the anomaly was not a message, but a byproduct, a natural consequence of universes vibrating within a shared structure. But this did not explain the alignment with future cosmological physics, nor did it explain the pre-inflationary placement. The puzzle grew deeper. Another group investigated whether quantum information could bypass the chronological flow of a universe entirely. In some interpretations of quantum field theory, entanglement can behave in ways that appear non-local, even timeless. Though entanglement cannot transmit information faster than light, its correlations hint at its connections underlying space-time rather than existing within it. If universes share an underlying quantum substrate, then information might not travel. It might simply persist, present in multiple universes simultaneously, expressed differently in each. In this view, the anomaly might not have been sent. It might have occurred an emergent feature of a deeper reality, but even this interpretation came with challenges. To explain the anomaly embedded within the cosmic microwave background, one would need a mechanism for information to manifest at the earliest stages of the universe's development, yet encode the physics of its far future. No existing theory offered such a bridge as simulations grew more complex and datasets more refined. A chilling pattern emerged. The anomaly's intervals suggested a cyclic behavior rhythm that expanded and contracted with mathematical elegance. The cycle did not reflect anything within the observable universe. It matched instead a hypothetical successor cosmos predicted in research papers, studying cosmic bounce, theories, universes that rise, collapse, and rise again. In these models, a universe nearing the end of its lifespan might undergo extreme compression, reaching densities so high that quantum effects dominate. In such conditions, remnants of it structured its energy fields. Its information could echo into a new universe. The anomaly looked like such an echo, but weeks of debate brought a deeper question to light. If this signal was indeed an echo from a successor universe, how could its imprint exist inside radiation released billions of years before that universe itself was born? This contradiction lay at the heart of the mystery, and as it hardened into consensus, the question shattered the last remaining conceptual barriers. The signal did not come from the past. It did not travel through time. It did not propagate across space. It appeared to enter reality through a pathway not contained. Within the fabric of space-time, all the only remaining interpretation was unsettling. The anomaly might be traveling through the deeper geometry of the multiverse, bypassing the chronology of individual universes altogether. The idea was almost unmanageable. In this framework, universes are not isolated timelines, but interconnected regions embedded in a greater geometric whole, a structure where time, as humans understand it, does not exist. Events in one universe could influence another not through cause and effect, but through resonance, interference, or geometric entanglement across higher dimensions. In such a structure, a universe's future is simply another region of the same landscape, not separated by time, but by position. From this perspective, the anomaly's presence before inflation made sense. It was not placed into the early universe. It was woven into the geometry that underlies all universes, appearing wherever that geometry emerges. It was not an intrusion. it was a footprint. This interpretation frightened even its proponents. It required abandoning the comfort of time as a linear river and accepting a reality in which universes are not sequences but arrangements, coexisting not in history, but in structured. In this vision, the signal was neither message nor mistake. It was evidence of a deeper order, a scaffolding beneath existence. The deeper scientists looked, the more the anomaly revealed itself not as communication, but as consequence. Not a deliberate act, but a resonance of cosmological architecture. What they had detected was not a voice reaching backward through time, but the shadow of a universe yet to exist, cast not into the past, but through the underlying geometry shared across all universes. It was the echo of a reality waiting to be born, and for the first time, humanity confronted the possibility that its universe was neither alone nor temporally isolated. Instead, it was part of a multiversal fabric where time does not bind, where causality is local but not universal, and where echoes of creation ripple across realities irrespective of their chronological sequence. In that recognition came fear, wonder, and a deepening sense that the anomaly was not merely a discovery. It was a revelation, one that would reshape humanity's place in the cosmos. It marked the moment the investigation shifted from understanding what the signal was to confronting what the universe itself might be. The deeper scientists ventured into the anomaly. The more the universe seemed to recoil, revealing layers of complexity that challenged everything they believed about existence. What began as a narrowband spike hidden in the cosmic microwave background had now grown into a phenomenon so elaborate, so profoundly structured, that it no longer resembled a signal at all. It resembled a system-an interconnected mechanism. Woven through the fabric of space-time, the first major shock came when the anomaly's internal rhythm was decoded. Researchers expected noise, perhaps a harmonic pattern associated with an exotic astrophysical source. Instead, they found something far stranger, a timestamp, not in language or symbols, but embedded in the modulation itself, an encoded reference point that aligned not with the age of the universe, nor with any known cosmological epoch, but with conditions projected to exist trillions of years into the future, in those remote epochs. Long after galaxies dissolve and matter thins to near nothingness, dark energy is predicted to dominate entirely, accelerating the expansion of space-time until all distances grow immeasurable. Stars will have died, black holes will evaporate, and even atoms may decay. It is a future where the universe becomes cold, silent, and nearly empty. Yet the anomaly carried the mathematical fingerprint of precisely that statan imprint of the universe, not as it is, nor as it was, but as it may become at the twilight of time. This was no longer a paradox. It was a rupture. Scientists had always treated time as a one-way cascade. Causes preceded effects. The arrow of time was secured by entropy, by the irreversible unfolding of events toward disorder. But the anomaly presented a timeline folded in upon itself, a future echo embedded in the oldest light of the universe. It implied that the cosmos not only ends, but transitions, perhaps even regenerates. Some models showed that a universe, upon reaching thermal death, might undergo a transformation, giving rise to a successor cosmos through quantum tunneling or through the rebound of spacetime itself. If such a successor universe existed, it might possess physical constants shifted slightly from those of its predecessor. And if it shared deeper geometric connections, it might leave faint imprints within the parent universe. Echoes of its future form. The anomaly's time stamp supported this idea. It was not arbitrary. It aligned with predictions for what physicists call a cosmic turnaround or vacuum transition, moments theorized to occur long after the death of stars. When spacetime itself undergoes a shift in energy state, it was a point where one universe could end and another begin. But how could information from such a distant epoch embed itself in radiation older than atoms? How could a successor universe inscribe a signature into a universe that existed trillions of years earlier? This contradiction gnawed at the scientific community, forcing them to consider possibilities that stretched far beyond established physics. The second shock came unexpectedly. As the anomaly was observed over months, small deviations appeared in its structure, not random variations, but subtle adaptations. The modulation shifted slightly, as if it were adjusting to something. The changes were minute, almost imperceptible, but consistent enough to be statistically significant. When researchers graphed the progression, the pattern formed a curve that seemed to respond to the very act of measurement. Some physicists dismissed this immediately as instrumental drift or algorithmic bias. But extensive tests ruled out that possibility. Independent observatories detected identical shifts, synchronized across different hemispheres and continents. The anomaly was not merely stable, it was responsive. A chilling thought emerged in late-night conversations, spoken hesitantly, almost apologetically. What if the anomaly contains a feedback mechanism? If the signal adapted to observations, it suggested an underlying structure capable of interaction. Not conscious, there was no evidence of intention, but reactive. Like a physical process influenced by conditions within the universe that detected it. This idea frightened even those who proposed it. If the anomaly responded to observation, it violated not only classical physics but also the principle of cosmic isolation, the assumption that universes, once formed, remain causally sealed from one another. A feedback mechanism implied a connection that existed outside time. Outside space, woven into a deeper architecture, the more the anomaly shifted. The more it appeared alive, not in a biological sense, but in a cosmological one, a living process within the geometry of reality. Something that sensed interaction and adjusted its rhythm accordingly. This deepened the most disturbing possibility. The anomaly was not an artifact of observation. It was a part of the universe's underlying operating system and emergent behavior of space-time itself. But the escalation did not end there. While the anomaly was analyzed through electromagnetic observations, a separate team working with gravitational wave data stumbled upon something extraordinary. Using detectors like LIGO and Virgo machines, designed to capture ripples in space-time from massive cosmic events, they noticed faint, low-frequency oscillations that mirrored the anomaly's modulation pattern. These oscillations were far too weak to resemble black hole mergers or neutron-star collisions. They did not originate from any known astrophysical source. Instead, they appeared as background ripples, space-time vibrations, synchronized with the anomaly's encoded intervals. This discovery sent shockwaves through every research team involved. Gravitational waves and electromagnetic signals operate on entirely different physical frameworks. For them to mirror one another, the anomaly could not be merely radiation or frequency modulation. It had to be something deeper, something that's embedded in spacetime's curvature. What had once been a localized signal became the signature of a cosmic phenomenon, the anomaly. It seemed it was not confined to the microwave background. It resonated through the fabric of space-time itself. This resonance changed everything. No known mechanism allowed information to imprint itself simultaneously in radiation and in space-time curvature. No model predicted it. No theory accounted for it. And yet the correlation was undeniable. At this point, the anomaly could no longer be understood as a simple signal. It behaved like a structural property, a dynamic pattern within the universe's foundational geometry. Its presence in gravitational waves suggested that it was not carried by particles or photons. It was carried by spacetime. Researchers began to confront an idea they had long avoided. The anomaly might be an emergent consequence of a multiversal architecture. It might not come from this universe at all, but instead arise from interactions with another universe embedded within a higher dimensional structure. In such models, universes are not isolated bubbles floating in emptiness, but interconnected regions of a much larger topology. Spacetime, at its deepest level, might be a lattice or a field where information flows not through time, but through geometry. If this were true, the timestamp was not a future moment in our universe. It was a coordinate in a larger geometric landscape, reference to a transformation in a different universe. One that has not yet begun from humanity's perspective, but has already occurred from the vantage of the multiverse. This interpretation was not metaphor. It was mathematics. physicists, studying eternal inflation, cyclic cosmology, and loop quantum gravity found that the anomaly's structure aligned with equations, describing transitions between vacuum states, mathematical bridges between universes. In these transitions, information can leak, resonate, or echo across boundaries, not as deliberate messages, but as natural consequences of geometry. The anomaly resembled such an echo. The more researchers analyzed it, the more the anomaly refused to fit any single category. Some insisted it was a message, a directed signal from a future universe, or an advanced civilization capable of manipulating space-time. Others argued it was a physical echo, a remnant of cosmic cycles imprinted across successive universes. Still others believed it was an emergent behavior of space-time's hidden architecture, something that no intelligence created, yet something no natural process within a single universe could explain. The debate grew more philosophical than scientific. Could information exist without a sender? Could a universe imprint its own future onto another? Could space-time behave like a resonance chamber, vibrating with patterns shaped by events that have not yet unfolded? The anomaly did not answer these questions. It only deepened them. One of the most troubling revelations came when a researcher plotted the anomaly's adaptive changes over time. The pattern suggested a form of stabilization, an attempt to maintain coherence even as instruments across Earth probed it more deeply. This was not consciousness, but stability-seeking behavior, reminiscent of physical systems that adjust to maintain equilibrium. Few dared to suggest that the anomaly behaved like a boundary condition, and anchor point between universes, a fixed pattern required for stability within a larger multiverse. If true, then observing it might introduce perturbations, triggering compensatory adjustments. This idea was unsettling. It implied that the anomaly was not only structural, but essential, that it was part of the deep architecture enabling universes to coexist. If so, probing it might reveal not just information, but the scaffolding that holds reality together. And as gravitational wave detectors continued capturing synchronized ripples, scientists began to feel that they were witnessing not an isolated signal, but the tremor of a vast, unseen mechanism operating behind space-time. Not intelligent, not alive, but profound. In private meetings, physicists spoke in hushed tones. Some believed the anomaly represented the first empirical evidence that universes interact through a higher dimensional landscape. Others feared that it was a warning that the boundaries between universes were thinner than assumed, vulnerable to disturbances. A few wondered whether the anomaly was the multiverse's way of regulating itself, a structural feedback system, ensuring continuity across cosmic generations. But no one could deny the escalating mystery. A signal that mirrored a distant future, a pattern that adapted as if aware of observation, a resonance captured in gravitational waves, a structure embedded not in space, but in space-time. These were not coincidences. They were revelations. Humanity had not merely detected a signal, it had stumbled upon the machinery of reality in the quiet moments between discoveries. A haunting realization emerged among the scientific teams. They were not studying a message. They were studying the universe's reflection, an echo cast across the geometry of the multiverse, carrying the imprint of what would one day exist. And the deeper they probed, the clearer one truth became: the anomaly was not asking to be understood. It was revealing that the universe itself is far stranger, far more interconnected, and far less bound by time than humanity had ever imagined. As the anomaly expanded from a faint curiosity into a global scientific reckoning, the search for explanation entered a realm of thought where mathematics blurred into philosophy and cosmology, brushed the edges of metaphysics. The universe, once assumed to be a closed system with neatly bounded laws, appeared porous, its boundaries thin, its chronology pliable. And in that new landscape, even the most speculative theories took on a new gravity. The first theoretical framework to gain traction emerged from the edges of inflationary cosmology, the multiverse interference model. In this vision, the universe humanity occupies is not alone, but one region of a far vaster, higher dimensional structure. Space-time is not a single sheet, but one layer among countless others, each expanding, colliding, or drifting in the eternal growth of an inflationary field. Between these layers exist boundaries, conceptual surfaces known as branes. They may be thin or thick, smooth or warped. Some models suggest that where branes curve too closely, information might leak between universes faint, distorted, yet detectable as anomalies in cosmic radiation. The anomalies' coherent structure seemed, at first glance, compatible with these ideas. If universes vibrated within a larger dimensional framework, then interference patterns could form naturally, much like sound waves merging in the air. The modulation of the anomaly resembled such an interference pattern, one that was not random but shaped by the physical properties of a neighboring universe. Although elegant, the model faced immediate challenges. Interference patterns between universes would likely be spatial distortions, not temporal signatures. They might warp the cosmic microwave background, create circular imprints, or produce regions of anomalous temperature, none of which match the anomaly's frequency-based structure. And no known mechanism within the multiverse framework allowed a signal to encode a timestamp from trillions of years into its future. Still, the model remained appealing. It provided a bridge away for information to pass between universes without violating the speed of light or the arrow of time. It suggested the anomaly was not a message, but the natural consequence of geometry. But even this idea paled before the second theory, the cosmic successor echo. In cyclical models of cosmology, the universe does not expand forever. Instead, it collapses under its own weight, rebounding into a new stata, cosmic bounce. After the collapse, conditions become so extreme that quantum fluctuations can seed the birth of a new universe, one that inherits the energy fields of its predecessor. In some variations of the theory, remnants of the parent universe survive the collapse encoded not in matter or radiation, but in the structure of spacetime itself. This framework made a startling prediction. Information from a future version of the universe could appear in its ancestral form, not as a message, but as an echo and imprint of what the universe will eventually become. Reflected backward through quantum geometry, the anomalies, stomp, aligned with far future cosmological physics, seem to support this model, as did the presence of low-frequency harmonics resembling the oscillation of scalar fields expected during cosmic rebirth. Yet the theory carried its own difficulties. A bounce event would create conditions so violent that no coherent signature should survive. The cosmic microwave background would be overwritten by the physics of the new universe. For an echo to endure from a future universe into a previous one, spacetime would need to operate in ways that defied classical causality entirely. Still, the cosmic successor echo presented a profound idea. Perhaps the anomaly was not from another universe, but from this universe, projected from what it will one day become. The third theory arose from the strange, restless domain of quantum gravity, information tunneling through quantum foam at the smallest scales far below atoms. Below quarks, below the fabric of space-time, exists a turbulent landscape known as quantum foam. It is a region predicted by quantum field theory, where virtual particles erupt and vanish, and where space-time itself twists and fluctuates chaotically. In this realm, the classical assumptions of time and distance break down. Some physicists believe that under extreme conditions, information might tunnel across space-time, bypassing normal chronological order. In this model, the anomaly's coherence and apparent forward time signature could result from fluctuations that allow information to slip outside the arrow of time, not backward, but orthogonally, through a dimension not bound by temporal flow. If such tunneling occurred, the information might appear in the early universe not because it traveled through time, but because it emerged from a deeper layer of space-time structure. The strength of this theory lay in its ability to explain the anomaly without invoking an external universe. The weakness lay in its extreme speculation. No laboratory experiment has ever verified the existence of time-free tunneling, and the anomaly's macroscale coherence seemed unfathomable for a process rooted in Planck-scale chaos. Yet the theory remained on the table. It was one of the few frameworks that offered a means for information to exist before space-time itself had fully formed. The fourth theory was darker, more unsettling, the false vacuum transition, according to modern cosmology. The universe may not occupy its lowest possible energy state. It could exist in a metastable vacuuma, temporary but long-lived configuration. If it decays, the universe could transition to a lower energy state in a catastrophic event known as vacuum decay. Such a transition would redefine the laws of physics, altering matter fields and space-time on a fundamental level. Some theorists proposed that the anomaly signature matched predictions of a universe near the brink of such a transition. If vacuum decay is inevitably, and many models suggest it is, then the anomaly might originate from the conditions that occur in the universe immediately after the transition. In this scenario, the signal is not a communication from a future universe, but a preview of what this universe will become when its vacuum state changes. But this explanation carried a chilling implication. If the anomaly came from a future vacuum state, then the universe might be closer to transition than expected. And because vacuum decay travels at the speed of light or faster, there would be no warning when it began. Most scientists rejected this interpretation, not because it lacked mathematical grounding, but because it evoked consequences too catastrophic to entertain casually. Yet the theory persisted in quiet corners of scientific discussion, a specter lurking behind more palatable explanations. The fifth theory emerged from eternal inflation, one of the most widely studied multiverse frameworks, the eternal inflation feedback loop. In this model, the universe is one bubble among countless others, each formed within a vast, inflating field. Child universes branch from parent universes, inheriting certain scalar field properties. In rare conditions, feedback loops can occur situations where the inflationary field dynamics allow information to imprint backward onto the parent universe. Not deliberately, but as a consequence of the scalar field's underlying equations. The anomaly's modulation resembled patterns predicted in simulations of such feedback loops. The frequency drift, the harmonic echoes, even the timestamp-like structure all aligned with possibilities arising from field interactions across cosmic generations. This theory had elegance. It explained the anomaly's presence in the cosmic microwave background. It matched the idea of universes connected not through time, but through inflationary geometry. It reconciled the anomaly's coherence with physical laws by placing the burden on the scalar fields that shape cosmic evolution. But it had a weakness. Scalar field feedback had never been observed, and if confirmed, it would imply that universes are far less isolated than assumed that events in one cosmic generation can reverberate into another. Finally came the sixth theory, whispered only after other explanations had been exhausted: the exotic intelligence hypothesis. This idea did not suggest aliens as traditionally imagined. Rather, it proposed that if advanced civilizations exist in future universes, with physical constants and energy states different from our own, they might manipulate space-time topology in ways indistinguishable from natural cosmological processes. In such a scenario, the anomaly might represent a byproduct of their technologies, their experiments, or even their attempts at communication across universes. The strength of this theory lay in its ability to accommodate intentional structure within the anomaly. The weakness lay in the absence of any evidence that intelligence can survive or arise in universes dominated by dark energy or near-cosmic rebirth. Still, the idea captured imagination. If intelligence exists beyond this universe, shaped by physical laws unfamiliar to humanity, its actions might resemble natural phenomena. The anomaly could be neither message nor accident, but the footprint of activity in a world beyond conception. As debates grew more intense, something remarkable began to happen. No single theory dominated. Each explained part of the anomaly. None explained all of it. The multiverse interference model captured the anomaly's resonance. The cosmic successor echo captured its timestamp. Quantum tunneling explained its pre-inflationary placement. False vacuum transition explained its future physics signature. Eternal inflation explained its harmonic structure. Exotic intelligence explained its adaptive behavior. The anomaly sat at the intersection of every theory and defied every one. It was as though the universe had placed a riddle at the boundary between science and philosophy, a question that exposed the limits of human frameworks. The deeper researchers probed, the more they began to realize that the anomaly might not belong to any existing theory. It might instead reveal a truth that requires a new category altogether. Perhaps the signal was not a message. Perhaps it was not an echo. Perhaps it was something more fundamental, a property of reality itself. Expressed across universes and ages, in the end, theories and speculations multiplied, branching into possibilities both wondrous and terrifying. But one truth united them, whatever the anomaly was. It had changed the human understanding of the cosmos forever. It marked the moment when humanity glimpsed not just the structure of the universe it inhabits, but the structure of the reality that contains all universes. In the months following the anomaly's emergence, the world of science entered a phase unlike anything in its history. For the first time, humanity's tools built to capture the faintest whispers of the cosmos were no longer merely instruments of observation. They had become instruments of interrogation, probing a riddle woven into the foundation of reality. Telescopes, detectors, colliders, quantum machines stood together like an orchestra preparing to perform a symphony no composer had written, guided only by the hope that their collective insight might unveil the truth hidden in the anomaly's impossible rhythm. The James Webb Space Telescope was among the first to respond. Suspended in the cold void beyond Earth's warmth, JWST had already revealed galaxies from the universe's early dawn structures. So ancient they challenged existing theories of formation. Now, astronomers turned its gaze toward deep field regions, searching for redshift patterns that might correlate with the anomaly's harmonic structure, if the signal truly echoed a future cosmological epoch. Still, the model remained appealing. It provided a bridge away for information to pass between universes without violating the speed of light or the arrow of time. It suggested the anomaly was not a message, but the natural consequence of geometry. But even this idea paled before the second theory. The cosmic successor echo. In cyclical models of cosmology, the universe does not expand forever. Instead, it collapses under its own weight, rebounding into a new stata, cosmic bounce. After the collapse, conditions become so extreme that quantum fluctuations concede the birth of a new universe, one that inherits the energy fields of its predecessor. In some variations of the theory, remnants of the parent universe survive the collapse encoded not in matter or radiation, but in the structure of space-time itself. This framework made a startling prediction. Information from a future version of the universe could appear in its ancestral form, not as a message, but as an echo-and imprint of what the universe will eventually become, reflected backward through quantum geometry. The anomaly's time stamp, aligned with far future cosmological physics, seemed to support this model, as did the presence of low-frequency harmonics resembling the oscillation of scalar fields expected during cosmic rebirth. Yet the theory carried its own difficulties. A bounce event would create conditions so violent that no coherent signature should survive. The cosmic microwave background would be overwritten by the physics of the new universe. For an echo to endure from a future universe into a previous one, space-time would need to operate in ways that defied classical causality entirely. Still, the cosmic successor echo presented a profound idea. Perhaps the anomaly was not from another universe, but from this universe, projected from what it will one day become. The third theory arose from the strange, restless domain of quantum gravity, information tunneling through quantum foam. At the smallest scales far below atoms, below quarks, below the fabric of space-time, exists a turbulent landscape known as quantum foam. It is a region predicted by quantum field theory, where virtual particles erupt and vanish, and where space-time itself twists and fluctuates chaotically. In this realm, the classical assumptions of time and distance break down. Some physicists believe that under extreme conditions, information might tunnel across spacetime, bypassing normal chronological order. In this model, the anomaly's coherence and apparent forward time signature could result from fluctuations that allow information to slip outside the arrow of time, not backward but orthogonally, through a dimension not bound by temporal flow. If such tunneling occurred, the information might appear in the early universe not because it traveled through time, but because it emerged from a deeper layer of spacetimes. The strength of this theory lay in its ability to explain the anomaly without invoking an external universe. The weakness lay in its extreme speculation. No laboratory experiment has ever verified the existence of time-free tunneling, and the anomaly's macro-scale coherence seemed unfathomable for a process rooted in Planck-scale chaos. Yet the theory remained on the table. It was one of the few frameworks that offered a means for information to exist before space-time itself had fully formed. The fourth theory was darker, more unsettling: the false vacuum transition. According to modern cosmology, the universe may not occupy its lowest possible energy state. It could exist in a metastable vacuum, a temporary but long-lived configuration. If it decays, the universe could transition to a lower energy state in a catastrophic event known as vacuum decay. Such a transition would redefine the laws of physics, altering matter fields and space-time on a fundamental level. Some theorists proposed that the anomaly's signature matched predictions of a universe near the brink of such a transition. If vacuum decay is inevitable, and many models suggest it is, then the anomaly might originate from the conditions that occur in the universe immediately after the transition. In this scenario, the signal is not a communication from a future universe, but a preview of what this universe will become when its vacuum state changes. But this explanation carried a chilling implication. If the anomaly came from a future vacuum state, then the universe might be closer to transition than expected. And because vacuum decay travels at the speed of light or faster, there would be no warning when it began. Most scientists rejected this interpretation, not because it lacked mathematical grounding, but because it evoked consequences too catastrophic to entertain casually. Yet the theory persisted in quiet corners of scientific discussion, a specter lurking behind more palatable explanations. The fifth theory emerged from eternal inflation, one of the most widely studied multiverse frameworks, the eternal inflation feedback loop. In this model, the universe is one bubble among countless others, each formed within a vast, inflating field. Child universes branch from parent universes, inheriting certain scalar field properties. In rare conditions, feedback loops can occur, situations where the inflationary field dynamics allow information to imprint backward onto the parent universe, not deliberately, but as a consequence of the scalar field's underlying equations. The anomaly's modulation resembled patterns predicted in simulations of such feedback loops. The frequency drift, the harmonic echoes, even the timestamp-like structure, all aligned with possibilities arising from field interactions across cosmic generations. This theory had elegance. It explained the anomaly's presence in the cosmic microwave background. It matched the idea of universes connected not through time, but through inflationary geometry. It reconciled the anomaly's coherence with physical laws by placing the burden on the scalar fields that shaped cosmic evolution. But it had a weakness. Scalar field feedback had never been observed, and if confirmed, it would imply that universes are far less isolated than assumed, that events in one cosmic generation can reverberate into another. Finally came the sixth theory, whispered only after other explanations had been exhausted: the exotic intelligence hypothesis. This idea did not suggest aliens as traditionally imagined. Rather, it proposed that if advanced civilizations exist in future universes with physical constants and energy states different from our own, they might manipulate space-time topology in ways indistinguishable from natural cosmological processes. In such a scenario, the anomaly might represent a byproduct of their technologies, their experiments, or even their attempts at communication across universes. The strength of this theory lay in its ability to accommodate intentional structure within the anomaly. The weakness lay in the absence of any evidence that intelligence can survive, or arisen universes dominated by dark energy or near cosmic rebirth. Still, the idea captured imagination. If intelligence exists beyond this universe, shaped by physical laws unfamiliar to humanity, its actions might resemble natural phenomena. The anomaly could be neither message nor accident, but the footprint of activity in a world beyond conception. As debates grew more intense, something remarkable began to happen. No single theory dominated. Each explained part of the anomaly. None explained all of it. The multiverse interference model captured the anomaly's resonance. The cosmic successor echo captured its timestamp. Quantum tunneling explained its pre-inflationary placement. False vacuum transition explained its future physics signature. Eternal inflation explained its harmonic structure. Exotic intelligence explained its adaptive behavior. The anomaly sat at the intersection of every theory and defied every one. It was as though the universe had placed a riddle at the boundary between science and philosophy, a question that exposed the limits of human frameworks. The deeper researchers probed, the more they began to realize that the anomaly might not belong to any existing theory. It might instead reveal a truth that requires a new category altogether. Perhaps the signal was not a message. Perhaps it was not an echo. Perhaps it was something more fundamental, a property of reality itself. Expressed across universes and ages, in the end, theories and speculations multiplied, branching into possibilities both wondrous and terrifying. But one truth united them. Whatever the anomaly was, it had changed the human understanding of the cosmos forever. It marked the moment when humanity glimpsed not just the structure of the universe it inhabits, but the structure of the reality that contains all universes. In the months following the anomaly's emergence, the world of science entered a phase unlike anything in its history. For the first time, humanity's tools built to capture the faintest whispers of the cosmos were no longer merely instruments of observation. They had become instruments of interrogation, probing a riddle woven into the foundation of reality. Telescopes, detectors, colliders, and quantum machines stood together like an orchestra preparing to perform a symphony no composer had written, guided only by the hope that their collective insight might unveil the truth hidden in the anomaly's impossible rhythm. The James Webb Space Telescope was among the first to respond. Suspended in the cold void beyond Earth's warmth, JWST had already revealed galaxies from the universe's early dawn structures. So ancient they challenged existing theories of formation. Now, astronomers turned its gaze toward deep-field regions, searching for redshift patterns that might correlate with the anomaly's harmonic structure. If the signal truly echoed a future cosmological epoch, then distortions or irregular clustering might appear in regions where gravity and dark energy subtly misalign. What emerged from JWST's surveys were not clear patterns, but faint hints, tiny deviations in redshift distributions, barely statistically significant yet persistent enough to draw attention. These anomalies were not proof. They were whispers, the kind that could vanish under stricter analysis. But they hinted at something, a possible connection between the anomaly and the geometry shaping large-scale cosmic structure. Meanwhile, CHIMA, cylindrical radio telescope array scanning the sky for fast radio, burst shifted part of its processing pipeline to monitor repeating frequencies aligned with the anomaly's interval. CHIME's wide field of view allowed it to observe vast regions simultaneously, capturing not just individual frequencies, but entire harmonic families. Its data revealed patterns that mirrored the anomaly's repeating cadence, scattered faintly but consistently across unrelated sky regions. These frequencies did not correspond to known astrophysical bursts, nor to terrestrial interference. They felt like fragments of a larger, unseen phenomenon, pieces of a cosmic rhythm threading through the universe. Across continents, the square-kilometer Arathos cojoined the effort. Still under construction, yet partially operational, it possessed sensitivity unmatched by earlier instruments. For SKA, the anomaly was not merely a curiosity. It was a target designed for its capabilities. Its dishes and antennas began scanning for low-frequency modulations that might reveal deeper layers beneath the anomaly's primary signal. And slowly, hints of structure emerged. Not language, not numbers, but something fractal patterns nested within patterns, harmonics within harmonics, as though the anomaly held its multiple layers of encoding. But radio waves were only one path into the mystery. The anomaly had already shown its presence in gravitational waves weak. Synchronized ripples detected by LIGO and Virgo, their detectors, designed to measure distortions smaller than the width of a proton, were now tasked with correlating the anomaly's harmonic cycle with fluctuations in spacetime curvature. Over weeks of analysis, a correlation emerged. Faint, fleeting, but real. For researchers accustomed to dealing with black hole collisions and neutron-star mergers, this correlation felt like hearing a whisper echo across a canyon, soft, improbable, yet undeniably part of the same voice. The discovery raised a profound question. Was the anomaly encoded not in radiation, but in spacetime itself? If so, electromagnetic tools alone would never unravel it. Humanity would need instruments capable of probing geometry directly, not merely light. This responsibility fell to the European Space Agency's upcoming LISA mission, the Laser Interferometer Space Antenna. Scheduled to launch within the decade, LISA would place detectors millions of kilometers apart, floating in formation through the cold emptiness of space. Its purpose was singular: to detect hypersensitive distortions in spacetime across frequencies undetectable. From Earth, the anomaly seemed designed for such a mission. LISA would allow scientists to test whether the anomaly's structure modulated gravitational fields, whether its harmonics resonated across dimensions beyond the familiar three of space and one of time. If LISA detected these resonances, the implication would be staggering. The anomaly would be not an isolated signal, but a structural property of reality, vibrating across the universe like a cosmic heartbeat. As astrophysical instruments dug, deeper quantum computing laboratories entered the investigation from another angle. Their task was daunting: simulate the long-term evolution of the universe millions, billions, trillions of years into the future, and explore whether the anomaly matched predictions arising from specific cosmological end states. Classical computers could not handle such simulations, but quantum machines, with their ability to explore multiple states simultaneously, offered a path into these unimaginable epochs. Researchers fed the anomaly's modulation into models simulating dark energy dominance, vacuum transitions, and cosmic collapse. The results were not definitive, but they were suggestive. In several simulations, scalar fields associated with future universe dynamics oscillated with frequencies strikingly similar to those embedded in the anomaly, where preview a mathematical shadow of the universe's distant future, coded not in events, but in the evolution of physical constants. The quantum simulations also revealed something stranger. In hypothetical successor universes, those born from bounce cosmologies, the anomaly's harmonic intervals emerged naturally from early-stage dynamics. These echoes, occurring in models where universes inherit structural properties from predecessors, mirrored the anomaly's repeating cadence. The implication was profound. The anomaly might not be the signature of a single future universe, but of a future cosmic generation. The insights from quantum simulation pushed scientists toward questions they had never expected to ask. Was the anomaly evidence of cosmic evolution across universes? Was it a byproduct of the multiverse's growth? Or was it a fundamental property of reality expressed whenever universes formed or dissolved? While cosmologists debated these possibilities, particle physicists turned their attention to the anomaly from yet another angle. Through the machinery of high-energy colliders, facilities like the Large Hadron Collider began searching for theoretical particles and fields that might serve as conduits between universes or between epochs. Their focus? Higher dimensional fields predicted by string theory, supersymmetry, and other frameworks that extend the standard model. These fields, if they existed, could allow information to propagate outside conventional spacetime. Experiments probing for missing energy signatures, exotic decays, or anomalies in particle interactions gained new significance. Even slight deviations from expected results were reinterpreted through the lens of the anomaly. Some researchers speculated that if the anomaly were tied to higher dimensional physics, traces of such dimensions might appear in collider data, subtle hints of unseen geometry shaping the universe's evolution. So far, no collider had revealed definitive evidence. But the search had only begun. Across all disciplines, the scientific community unified around a shared set of questions that now defined not just research agendas, but humanity's pursuit of reality's deepest truths. Was the anomaly evolving over time? So, was its evolution intrinsic to its structure? Or was it responding to conditions within the universe that observed it? The idea of evolution carried implications far beyond typical signals. It suggested dynamic behavior, suggested interaction. Were the anomaly's harmonics hiding deeper layers of encoding mathematical structures that, once deciphered, might reveal their origin? So, they could be the key to understanding. Whether the anomaly was natural or emergent, accidental or structural, was the anomaly correlated with the cosmic neutrino background, another relic of the early universe, far older than the cosmic microwave background? If neutrinos carried similar anomalies, then the phenomenon might predate even the universe's thermal equilibrium, extending into epochs humans could barely conceptualize. And perhaps the most unsettling question of all, did the anomaly predict the fate of the universe? If its timestamp was indeed aligned with a future cosmic epoch, then the anomaly might be a map-a blueprint of what the universe will become. It could forecast the transition to a new vacuum state, the collapse of cosmic structure, or the birth of a successor universe. What might represent the universe's own trajectory, the echo of its future woven back into its past? But such interpretations were not conclusions. They were possibilities, windows into an understanding of the cosmos that had only just begun. What scientists understood now was simple. They had not reached the limits of their tools. They had reached the limits of their imagination. The anomaly had opened a new frontier, one where instruments built for a single universe now reached into the geometry of many, where gravitational waves, radio frequencies, quantum simulations, and high-energy collisions all converged on a single question. What kind of reality allows a universe to hear the echo of its own successor? For the first time, humanity was not merely observing cosmic history. It was observing cosmic architecture. And as the anomaly continued its steady, impossible rhythm, the world's instruments kept listening, each measurement a deeper descent into the unknown. The frontier had shifted, not outward into space, but inward into the nature of existence itself. And the mystery had only begun. There are moments in the human story when discovery does more than shift the boundaries of knowledge, it shifts the boundaries of existence. It asks humanity not merely to interpret new data, but to reinterpret itself. And as the anomaly continued, its impossible rhythm steady, ancient, and yet impossibly young, the world stood before such a moment. For centuries, time had been imagined as a river, flowing from a single source toward an unknown end. It carried all things with its stars, galaxies, civilizations, sweeping them onward in a current no force could reverse. From the first astronomers who charted the heavens to the physicists who mapped space-time, the direction of time remained absolute. It governed every law, every life, every dream. But the anomaly had revealed a truth far stranger. The river was not a river at all. It was an ocean vast, layered, and deep. And beneath its surface, currents ran in directions no human had. Future were not endpoints of a line, but regions of a landscape too immense to be grasped. A landscape in which universes rose and fell like waves, each part of a larger cosmic tide. As scientists paused from the calculations, the models, the simulations that filled their days, a quiet awe settled in. It was not the awe born from seeing something vast, but from feeling something vast. The realization that the anomaly might not be a message, but a memory from a universe that did not yet exist, but would one day arise from the ashes of this one. The emotional weight of this possibility was immense. If the signal was real, humanity had touched something beyond existence, beyond chronology, beyond the limits of matter and space. It had reached into the architecture of reality itself. Some researchers described the feeling as standing at the edge of a cliff, staring not into darkness, but into light from a world yet unborn. Others described it as hearing the faint echo of one's own footsteps from a path not yet walked. Whatever the metaphor, sentiment was the same. The anomaly had violated every boundary humanity believed, separated the present from the future, the known from the unimaginable. The signal did not merely hint at the future. It carried the fingerprints of it. But with that knowledge came humility. The universe, it seemed, was not a singular event. It was not a lone creation. Instead, it might be a cycle in endless rising and falling, a breathing of reality across spans of time so vast they defy language. One universe might give rise to another, and another after that, each inheriting subtle imprints from the one before it. And perhaps, in ways no theory yet describes, each new universe sends a ripple backward, not through time, but through the deeper geometry that links them, humanity. Long convinced of its position as observers of the cosmos, now faced the possibility that it was also observed not by beings, not by civilizations, but by the universe itself, folding its own future into the remnants of its past. It was a humbling thought that everything humans believed to be a beginning might be the continuation of something older, and everything believed to be an ending might merely be the seed of something yet to rise. Some philosophers turn their attention to the deeper implications. If the anomaly was an echo from a future universe, then the boundary between creator and created blurred. Did universes remember themselves? Could patterns, harmonics, and fields persist across cosmic generations? Was the anomaly the universe reflecting upon its own nature, like a mirror cast across epochs? Scientists, too, found themselves asking questions they never expected to confront. The idea that universes might form a lineage, cosmic ancestry stretching beyond any timeline, shifted the foundation of cosmology. No longer were researchers studying a single universe. They were studying one chapter in an epic series of realities, each shaped by forces beyond comprehension. And if universes were connected through some deeper fabric, what then was time? Was it a boundary, a dimension, or merely a human interpretation of something far more fluid? If time behaved differently in deeper layers of the multiverse, then perhaps the anomaly did not travel from the future at all. Perhaps future was simply the wrong word, a term, to bound to human experience to describe the true nature of reality. In this poetic uncertainty, something remarkable happened. People began to speak not just of the anomaly's scientific implications, but of its emotional ones. For those who looked through telescopes, time had always been a distance light years defined by how long photons took to arrive from distant stars. But now, time felt like a shape, a form, something with texture and depth. A medium in which echoes could drift, resonate, and return. Some wondered whether the anomaly represented a deeper truth, that reality itself might be layered with memory, just as the rings of a tree contain traces of every season it has lived. Perhaps the universe carries within it the traces of every universe that came before it. And if so, perhaps the anomaly was one such trace, a fossil from the future preserved in the oldest light. Others took the idea further. If universes rise and fall like waves, then what role does consciousness play? Does intelligence emerge only within individual universes, or is it part of a larger evolutionary rhythm? Could awareness, even in its simplest form, be a phenomenon that transcends cosmic boundaries, leaving imprints not in biology, but in geometry? These questions were not answered. They were amplified. And in their uncertainty, humanity found itself gazing at a cosmos far stranger and far more beautiful than previously imagined, as the anomaly continued its soft modulation. Responding subtly to observations, its behavior began to inspire a new kind of inquiry, one guided not just by physics, but by wonder. Researchers realized that the anomaly had not merely challenged their models, it had challenged their assumptions about existence itself. Why should time flow only forward? Why should the universe be alone? Why should creation be singular? Perhaps these were human questions, not cosmic ones. Perhaps the universe did not obey a single arrow of time, but many. Perhaps it did not end, but changed form. Perhaps creation was not an event, but a rhythm, a pulse echoing across realities. And if these reflections held any truth, then humanity's place within the cosmos shifted profoundly. Humans were not passengers drifting through a single timeline. They were inhabitants of a universe embedded within a structure of universes, each connected by hidden architecture. A larger truth began to crystallize. The anomaly may not have been sent. It may not have been deliberate. It may have been simply the consequence of a universe existing within a greater reality, one whose laws transcend human understanding. But even if it was not sent, it carried meaning. For it revealed that the cosmos is not silent. It speaks in harmonics and frequencies, in ripples and echoes. And occasionally, if humanity listens carefully, it allows a glimpse of what lies beyond. So the chapter closed, not with certainty, but with quiet reverence. For the first time, humanity stood before the idea that its universe is part of a greater continuum. That time is not a straight line, but an ocean. That reality is not a single story, but an anthology written across countless worlds, each rising and falling like waves in a boundless sea. And in that vastness, humanity understood something profound. The signal was not a whisper from the past. It was not a relic of the beginning. It was an echo of what the universe will one day become, a reflection of a world waiting in the depths of time. A universe not yet created, yet already leaving its imprint across existence. Humanity listened, and in that listening discovered not only the nature of the cosmos, but the possibility that the future is not distant. It is intertwined with every moment. It's every particle, every field. The universe had reached across its own timeline. And for the first time, humanity realized it was hearing its own future calling back.